my timer now so that I know that when I can take some time doing my slides. So I'll try and be on time and leave some time for questions at the end. There's a got it screen on here. Okay, so about me. First of all, there's a very awful picture of me, and I'm Nicky Dinsey. I'm the IT director at Abingdon School. I've been working here for about 7 years now. And today the presentation is going to be on an introduction to AI. It's a presentation I took from Inset, which is a like a teacher training day that we have 3 times a year at the school at Abingdon. So what I've done is kind of tried to intersperse some slides from that presentation into a kind of wider set of slides about how the history of large language models came about, all of the papers that, the key papers that made it happen. I was hoping to do more on thinking fast and slow, and there's other things that I'd like to do as well around alignment and medical processing and things like that. Some of that will have to wait for the extended workshop that's happening in March. But yes, so without further ado, before I can start talking about artificial intelligence, you really need to know about computer programming. Again, some of these slides may be a little bit simple for some of you, but just really this slide here kind of gives you an idea about how programming has worked since the start of all programming. Effectively, it's just logic. It's steps like if you do this, and then end. And if it doesn't do that, then follow on to the next track, etc. Follow through and error out is the main thing. Some of this stuff can be really quite fallible. There's a case in the UK that's been in the news at the moment where there's a computer system called Horizon at the post office was calculating incorrectly the amount of money that each sub postmaster was making each day, and these people were trying to do their figures and the computer was saying one thing, and lots of them ended up going to jail and things like that. But it's all based, because these systems are based on logic. They're based on just simple instructions that we've programmed into the computer to do. Artificial intelligence, on the other hand, and again, this is one of those more simple slides. Artificial intelligence, on the other hand, is the simulation of human intelligence in machines. It's these things here. It's these neurons that act as a neural network, whereby it's basically a large mathematical function where effectively you have an input and you have an output, and in the middle, over time, it decides to apply weights and biases to different neurons in the network to decide and learn and think. So they've been allowing us to do lots of things for a very long time now, like learning and problem solving and some reasoning. But yes, there is a lot to be said about the fact that a number of these layers in the middle are hidden. We don't really know generally why a particular neuron would be given more weight than another neuron in the model. But yes, that's what artificial intelligence is. And by programming these things, by training them, they end up being able to think and learn for themselves. Okay, so a little bit more. Thank you, Fordham. Let's quickly start with the history of AI. So AI, artificial intelligence, the term, the entire discipline was started by John McCarthy and Marvin Minsky back in 1956 at Dartmouth College, Hanover in Hampshire. It's something that me and John have spoken about at length, and was one of the inspirations for him and something called the XML Summer School that runs in Oxford over the summer. The idea of the Dartmouth Summer Research Project was that over 8 weeks, they had a number of different people who would spend all day, every day, talking about trying to come up with this AI, this artificial intelligence, through trying to mimic how the human brain works. There were 11 main attendees over the course of those 8 weeks, but another if you go to Wikipedia or whatever, there's stated there's 47 people in all kind of dropped in and out during the actual during the workshop. They included people like John Nash, who's famous from the film A Beautiful Mind, if you know who he is. But yeah, these are the main two guys, John McCarthy and Marvin Minsky. So after 10 years, interest in the field between 56 and 66. Um, things were working, but they weren't going very far. There were lots of setbacks and failures in how they could get these things to work. They couldn't work anything out. And we entered what is coined the AI winter or AI winters. There were breakthroughs during those years between 1966 and 2005. But in the most part, things were happening at a snail's pace, a very, very frozen pace. One of the key things that I'd like to make you aware of is IBM's Deep Blue. I don't know if you've heard of this. It's a computer system that in 1996 for the first time ever defeated the world chess champion Garry Kasparov. And the thing is, you need to remember about chess, though, is that it's a finite game. It might be exponential, as in, there's an awful lot of moves in chess that could possibly be played. But at the end of the day, it is something that could be effectively brute forced to make work. That word will come back for us a little bit later. Again, this is another slide from the inset. So finally, in 2005, up until the present day, we've entered what they call an AI summer. The main reasons for this is that there's now an awful lot more computing power, more compute available in the world. And there's been significant investment by companies like Amazon and Google, etc. Yes, in 2017, and I'll talk about this a lot more later, but there was a breakthrough in natural language processing that people didn't see coming at all. And that's kind of led us to where we are today with generative artificial intelligence. We'll return to this lot a bit later on. Okay, so before we go much further, I just wanted to, again, another slide from my presentation to the teachers and headmasters here in the UK. I just wanted to talk about levels of AI. So the first level of AI is called narrow or weak AI. This is something that effectively just specializes in one particular function, whether that be translation, a voice assistant like Google, like Amazon's Alexa, face recognition systems being used in China to, spy on their populations, on their citizens. Yes, so that's what narrow AI means. It means it's something that's been trained to do one particular thing. The next level, which has got everybody in a lot of excitement at the moment compared to where we are in the last couple of years, is something called artificial general intelligence. This is the idea of having a computer match the intelligence of a single human brain. Sam Altman from OpenAI calls this the median human. This is the idea that effectively you can get a computer, a model like ChatGPT or whatever, to act and manage most human tasks. Yeah, so a lot of people are the idea of getting AGI was quite some way off originally. But where this actually is going to happen, what year it's going to happen, seems to be coming down year and year. Some people even think it might happen this year. After that, you get something called artificial superintelligence, which is effectively where AI is as good or exceeds the intellect of all humans, all 8 billion of us on the planet. They kind of wax lyrical about the fact that this might unravel the different scientific mysteries and how the universe works. It will open up things like quantum computing, longevity, so we'll live forever. And nanotechnology and things like this, leading to something that's the actual term coined, which is the technological singularity, where we no longer have to work post-labor economics, et cetera, et cetera. I'd like to kind of bring you back down to earth a little bit for a second. We're a long way away from a Wall-E style universe. We are very, very much with AI at the moment in what Gartner calls the hype cycle, where effectively we've had an innovation trigger. We're somewhere on this curve at the moment, but at some point it's going to reach its peak, and then it's going to have this kind of drop down before it starts to slope back up to where the plateau of productivity is. So I just wanted to make you aware that some of the news about people's jobs and things like that are definitely something to worry about, but this idea of everything taking over is a little bit far-fetched for the time being. Okay, right, moving on to the next section. So let's talk about generative AI. I want to talk about two main topics today. One of them I'm going to go over relatively quickly, and that's image generation. And then we'll talk about large language models after that. Okay, so image diffusion. There are three main kind of competitors in this market at the moment. I don't know how many people have actually played with this stuff before, but there's DALL-E from OpenAI. There's Stable Diffusion, which is an open source diffusion model where you can actually download the models and perform the calculations on your own computer or on a computer in the cloud. And then there's something called Midjourney, which is very, very popular on an instant message platform called Discord. So how do these things work? Well, what happens is that you give the AI, in this case, pictures. You give it pictures like this one here. This is a picture of a cat who's got white paws on a table. It's got an office background. There's blinds there you can see in the background, and there's a bit of a red sofa or something in the background. You effectively take pictures of cats, thousands of pictures of cats, millions of pictures of cats. There are a lot of cats on the internet. And if you take those pictures, input the text that describes what's in the picture, and then slowly turn that picture into noise, you train the AI model to understand what makes up those pixels to make that image for you. What you can then do is reverse the whole situation around. So once you've trained your model, you effectively give it some noise and your prompt. We'll come back to what prompts are and everything later, but you give it the same prompt, and then slowly over a number of steps, it will turn that noise into a picture like this, which is a cat with white paws on a table, office background, blinds, and a red sofa. So it's learned all of these different objects and then is able to actually kind of combine them all together. There's a lot of highly technical things behind this. So I just want to say that I've given you a very simplistic view, but this is well beyond scope of what we're going to talk about today. But effectively, as I say, it's in with some static, and then it turns that into the picture over a number of steps. And the pace of change here has just been phenomenal, guys. So one thing that Midjourney allows you to do, it allows you to use the different versions of Midjourney since it was created, versions 1 through 6. So I took a statement here that said, a friendly headmaster of an English boys' school. We're a boys' school here at Abingdon. And we use the version using that same prompt on all the different versions. It gives you 4 pictures at once when you run this stuff. So this was the first version back in February 22. You see the third version, second and third versions here kind of coming together. On this version here, so by March 23, a year later, it was producing pictures that were effectively photorealistic. I don't know if you can see that zooming on your screen, but yes, the pictures themselves are phenomenally well described and well imaged. Eventually, in version 6, which was released just before Christmas last year, obviously Midjourney had gone a little bit Harry Potter on us, taking that same prompt and was generating images of this description. Another thing you can do with images is that you can this is what we call text to image. You can also do image to image as well. So going back to that rather awful picture of me at the start of the lecture, you can see that by passing in that picture and then a prompt of the site, which is younger with hair in a cartoon style, it kind of generates this based on my features, etc., and what I'm wearing and the lanyard, etc. You can see the background. It's attempted to try and recreate the background, as well as giving me a very fresh looking face and a lots of hair there. So this technology has come on in leaps and bounds, and it's amazing what people can do with these things today. Okay, so moving on. Large language models. So this is where we start to get a little bit more into the technical stuff for today. So the origins of LLMs, the origins of large language models. So back in 1986, Michael I. Jordan produced a very inspired paper called the Serial Order, a Parallel Distributed Processing Approach. And this is a neural network here. He trained it on a sequence of letters to produce a pattern. But the key insight that this paper has done, that had been missing for the previous 20 years, was that he added these extra neurons here, which are called state units. And it allowed the output from the network to feed back in to the network and then back through the model. So the input comes from here and then goes through the model once, and then it gives it effectively a memory, or what we now call the context, which is going to be very important later on. So this key insight allowed him to effectively push so after training out on the characters A, B, it allowed him to pass the first character in, and it would go through the network, learn and know what it has to do, and then push the next character out, another A, and push it into here, and then another A, and then a B, as it were. And yeah, it appeared to work. So 5 years later, in 1990, John Elmond continued Jordan's work. And at this time, the paper was called Finding Structure in Time. He trained it on an even bigger network, this time 50 neurons, and he trained it on language. So he gave it 200 short sentences, and and then streamed those in one by one. He didn't give them as words; they were literally given as individual letters again. And they had no spaces. There were no boundaries as there were between the words. But each time he trained the network, he would give it this reinforcement learning, which we'll come back to in a little while, to train it to say, yes, you're doing the right thing. No, you're not. You're doing the wrong thing, etc. And as you can see here from this plot that he made, that the system seemed to learn, let's turn on the laser pointer, the system seemed to learn the word boundaries on its own. He didn't program it to do this. It simply worked out, there's many, and then years ago, you can see that it worked out these boundaries on its own, which is pretty amazing stuff, and he was quite impressed by this. So he moved on and started to probe the network itself. So after he trained it on these things, he was able to kind of work out that by looking inside the network, looking inside the hidden layers, as it were, that the context, how the actual neural network had worked, it had actually spatially clustered the different words into verbs and into nouns, and then subcategories within that. It was able to actually work out that this is a group of effectively inanimate objects, and then some are food, like sandwiches and bread, and some are breakables, etc. And really, how could such a little network, remember this thing's only got 50 neurons, able to start to understand these words semantically? And so, yeah, according to Chomsky, and I had to cut some of this stuff from the paper. I think I'll come back to Noam Chomsky in the bigger lecture. But Noam Chomsky, didn't say that this was the way that you actually, the children learn to talk or learn to think. And it appears, or Elman says, was that everything can be learned from patterns in the language itself. So back to some of the slides that I gave to the teachers for a second. So let's just look at what we've done here. It's not next word prediction at the moment, it's next letter prediction. But what you do is you train an AI on large amounts of text. You then ask the AI you give an input like this, and then you ask the AI to predict what the next letter is going to be, and then you train it to increase those weights by rewarding good decisions and penalizing bad decisions, effectively giving it a reward. And this term is called reinforcement learning from human feedback. So that's the way that this stuff works. And it's very closely aligned with how babies learn to talk as well. So I've got a very small video here where you can see a baby actually trying to talk to the other baby. Yes, so this is effectively how we're training AI in a very similar way to how you teach baby humans to learn. Okay. Elman continued though. So from here, he started to say, well, if we've got nouns and verbs and subcategories, what he also made a discovery on is around the fact that sequences of words or sentences are effectively, they follow a pathway. And similar similar. So there is a process to how a sentence is made up, and those sentences are very similar. So similar sentences will follow similar pathways, as it says here. And it's kind of true to think about as well about how the human brain has pathways of thought. So if you pause for a second and think about how it's possible to, when you're actually focusing on one particular action, one particular task or whatever, you have there's different layers of thought pathways going on inside your brain. So this was all, back in 1990, of course. So yeah, hopefully you can start to see where I'm going with this little extra bit in the middle here. But really, for a decade or so, nothing kind of happened at all. These problems were considered, these findings were considered just as simply toys. They didn't really do anything. They didn't really know what to do with them, and certainly we did not have the processing power to do anything really much bigger at all. But then there are further enhancements started to happen, and one of the key enhancements was nearly 20 years later from that paper in 1990, which is generating text with recurrent neural networks. It's from the University of Toronto. Ilya Sutskever is one of the leading researchers at OpenAI. Jeffrey Hinton, another godfather of AI as well, was working on this paper, but it had a relatively mundane application. It was actually to kind of say, well, what happens if you use these language models to kind of effectively allow you to compress text inside a document, and much like a zip file, but instead you could actually start to make it feel like you could literally miss words completely out. I've got something from John Hopfield here, very, very quickly, but like.
I'll see you every second for the next hour or what have you. Each look at you is a little bit different. I don't store all those second by second images. I don't store 3,000 images. I somehow compact this information.
And this is what they were trying to go for. So, and it's absolutely true. If you think about your mind and the way that the brain works, you don't remember everything about a conversation or a night out, or depending how much you've drank, how much of that night out. And this is kind of what they were going for with this particular paper.
I'll see you.
Let's turn that off. Here we go. So let's follow on this paper a little bit more. So they basically in 2011 they were able to train it on a much larger amount of training data. This thing had thousands of neurons and millions of connections in between, but it still follows this same kind of memory process which we showed before back in the 80s, 1986. And effectively, you pass in the start of a sentence that the meaning of life is. And what they found was that, the system, and this is straight from the paper, this wording here, is that the tradition, so the meaning of life is the tradition of the ancient human reproduction, came out of the network. And it was astounding to them, absolutely astounding to them, that they were able to get something coherent and make sense by just asking it to predict what the next word is, and this RHLF reinforcement learning. But of course, simply after a few words, the thing would actually just turn off into gibberish. So this is the following part of what it said. So, it is less favorable for a good boy. It just makes absolutely no sense, starts to produce characters and symbols in the way. So what they were thinking is that, with a bigger network, it might just be possible. This language model idea might just be possible to brute force higher standards of performance and, get to some kind of AI via just next word prediction alone. Okay, so a few years later, 3 or 4 years later, Andrei Karpathy released a blog post. I don't think this was a paper. This is the only one that's not a paper, a research paper on here. But in 2005. Andrei Karpathy, amongst other things in this blog post, took the same, it built on what OpenAI had done, the University of Toronto had done earlier, and said, okay, well, what happens if I train it on all of Shakespeare, train a language model on all of Shakespeare? How would we see, instead of just doing words, but can it do the structure, the style of the writing itself? And after a short amount of time, a few hours of training, only a few hours, this is 2015, it was able to actually start producing very almost barely recognized these as samples from actual Shakespeare, as you can see here. It effectively was able to just spurt out words that seemed like they were the real thing coming from Big Bill over here. So what Karpathy also did is he noticed that, learning organically, you didn't have to program the network. It effectively, again, this is very early on, but he was looking at deep learning and thinking, well, I'm setting up a system with a broad goal, learn to speak. And then once it's trained, I can retask on a narrow goal of, write a sonnet without actually having to sit there and program in that very traditional method of, logic and ifs and else's and all of those kind of things. So yeah, this was an amazing discovery, and it was picked up quite quickly. So there was a turning point in 2017, so a couple of years later. And this is OpenAI first entering the fray. Ilya Sutskever has now left the University of Toronto and he's working for OpenAI. I think he worked at Google as well. But OpenAI built on Karpathy's work now. So they get, well, what happens if we make it even bigger? So we'll take every Amazon review that we can possibly lay our hands on. 82 million Amazon reviews. It was the largest network that had ever been trained to date. When they probed the neurons, a lot like Elman did back a few slides ago, they came across an amazing discovery. It's something that nobody ever thought would happen. That a single node, a single neuron, inside this model seemed to be by the AI have been assigned the job of sentiment. So sentiment in this case is whether or not the sentence that you're looking at that is read is positive or negative. And it seemed just completely bizarre to them that they could pass in one of these Amazon reviews, and this sentiment neuron would effectively turn on or off in the middle of it. It was an amazing discovery, and to kind of help them kind of understand that they and again, this is from the paper. They assigned a color to this on-off switch, or effectively it looks like a float to me. So you can see here that this comes straight from the paper, which sentences are it thinks are negative, like this from a crappy script, as you can see here, crappy story, crappy acting, etc. Obviously that's highly red, and then there are other sentences which are highly green as well. So this was really something that the industry at large. In fact, I worked for a company at one stage called 1,000 Heads 15 years ago that would have people looking at tweets and trying to decide whether or not for their client the tweet was negative or positive about it. This natural language processing 15 years ago required lots and lots of people to look at these things and classify the text. And all of a sudden, emerging out of this model, out of what they've trained, was a neuron that they could effectively see whether the text that you put into it is positive or negative. And this is a first instance of what we want to say is like a proper emergent property of a neural network. Okay, so continuing on with this paper, they also managed to manually switch this neuron on and off when asking the thing to generate some text. And as you can see here, obviously the slides will be shared with you afterwards, but you can see that if you turn the sentiment neuron on, it would start producing Amazon reviews that were as good as any Amazon review that you're going to see on the website, and they would either be positive or negative, which was just absolutely unheard of at the time. Okay, there were some things about final work and stuff like that. I do want to speed up a little bit. But yes, so just coming back to this original idea of passing the input back in to these state units and the context. There was a problem with this. So, with 80 million Amazon reviews, the problem is that this is a linear type of memory, a serial memory, and effectively it was coming up against a bottleneck. They simply couldn't train a network anymore because it was just taking up too much memory, too large, and that meant that they really couldn't extend the ability for it to actually keep coherence, or what they call context, or you can pass in longer sentences and longer things. So Luckily enough, in the same year as that previous paper, Attention is All You Need is an absolute groundbreaking paper. So hold on to your papers, fellow scholars here. This one came out again from Google. And they just released this to the world, so everybody got to see it. But it introduced to the world something called transformers. Now, transformers themselves are probably out of scope in real depth for this lecture, but there are some things I want to talk about for you. So first of all, the first thing that it meant is that you could reduce to one layer in the network what used to take many, many, many layers. Okay, and this is something called a self-attention layer. It did away with the state units that you saw on the previous page, and added a self-attention layer that allowed it to actually look back in on itself. This resulted in a shallower but wider network. So this gets wider and wider, which makes it much more practical to train at scale. So we can go from 82 billion Amazon reviews to, well, you'll see a little bit later. Okay, another thing about transformers is something called the attention heads. So again, I'm not going to talk too much about these right now. I think there's one more slide actually. But attention heads, in a nutshell, what they do is they act as a lens on every word. So every word in a sentence has a different meaning in a sentence and in the context of where you're actually learning it. It's the semantic context and meaning. So there's a great visualizer here, which you can go and look up online, which allows you to effectively create a sentence and see how the tokens, as they call them, the words themselves, relate to each other within a sentence. So this adds even more knowledge to the model, and works really, really well. So what this means is that you've gone from a model which you have to pass everything back through in a linear fashion back into itself through these state units, into something where a neuron can look at everything everywhere all at once. And I've got a great visualization for you here. It's a minute or so long, but it does tell you, it does kind of give you an idea. So this is a video of an AI playing a piano, and then having to look back on itself to actually kind of understand what it's said before and what it's going to play next. So you see, oh, it went back a bit. Oh, there we go. So you see, it fell over a little bit in the middle there. So this is AI. We're still learning and all that kind of stuff to make these things right. But you could see that how each time it played a note, it had to look back on itself to kind of decide whereabouts in the sequence of the notes it actually was. And this was a phenomenal change. I just want to talk about concept space. So keeping together with these things about. This is coming back to the idea of attention heads and word semantic meaning. And so you take a word like bank, and if you imagine this is like a big word space where you've got lots of words, bank is more related to money. In most situations, you'd think of bank and cash and things like that. But they can also be related to river, as in riverbanks. So when you push in the statement, the river has a steep bank, the attention heads, the lens of each word can look around itself and actually see how in this context, in this semantic context, bank is much closer related to the word river than it is to money. So I hope that makes sense, but it's a key point from the paper. Yes. So once they'd actually once OpenAI had we're in the attention is all you need. One thing to remember about this paper, the Transformers paper from Google, is they're still stuck in what's called the old paradigm, where they're trying to train an AI to effectively learn a singular task. In this case, it was to learn how to translate between different languages. And what they discovered, in the paper is phenomenal, is that you could translate flawlessly between different languages using this new method. But yeah, as I say, it was stuck on this narrow task. Of course, Ilya and the OpenAI lot read this paper, which was just produced, put out on archive like everything else, and they picked it up immediately and applied it to transformers to what they'd been doing with next word prediction. All right, here we go. So enter GPT. We're starting to get towards the end of the presentations, as I'm sure you can see. Enter GPT, so generative pre-trained transformers is the paper released in 2018. This is GPT-1, everybody. So GPT-1 came out from in that year, and they trained it on 7,000 books. And they applied this transformer architecture. And were able to, crucially, they were able to extend this context window. So things didn't fall apart after 3 or 4 words as it was previously doing. And for the first time, they started to see that the model was starting to display abilities beyond what it had learned in pre-training. So what do I mean by that? So effectively, you could start to do something called zero-shot learning. So you have a pre-trained model, which has spent hours cooking away on GPUs in the cloud, training it on books and everything else. And then you could ask it, and once it's finished, you have this kind of context window whereby you can learn, you can ask it questions, not just like we saw before, the meaning of life, and ask it to finish a sentence, but you can actually ask it questions that weren't in the original training data. So this was a massive discovery. The fact that you could say something like, is glass breakable, and get out of it, yes, glass is highly brittle and easy to break. And yet you had not trained it on those statements. It wasn't in its training guide. It just learned this itself. So enter GPT-2 and GPT-3. I think really the point here is that before we get to GPT-2 and 3, OpenAI kind of released this paper, and it was basically mostly ignored. At the time, the thing is, people just seem to see this stuff as a toy. It's like it was just a trick, because it drifted off into nonsense. Started making up, losing coherence, losing context. People weren't really interested in it back in 2018, but they moved on. They worked hard on it, and they said, well, we're going to keep brute forcing this thing. We're going to make an even bigger model. We're going to make an even bigger model, and we're going to train it on literally everything we can get our hands on. So things like Wikipedia and Reddit were easy sources of large amounts of data at the time. And there's something called the Common Crawl, which is effectively the entire internet bundled up in a few terabytes of data. And eventually as well, so those were things they were doing with GPT-2, and then GPT-3 comes along. Eventually, they were out there scraping literally every open website they could lay their hands on to put into the training data, and then go through this training process of reinforcement learning from human feedback. And this brute forcing approach of just literally just throwing the absolute kitchen sink at it did have, and crucially, this increasing the context window where you can actually type in and give it instructions, actually gave it more emergent properties. You're now able to teach this model properly to do things after the training part of the process was frozen. And this in-context learning, as they call it, allows the model to do things that hopefully most people have tried and seen today, where we can ask it questions and things. One thing they did do in this stage in GPT-3, I think it was something called the WUG test, which is a milestone in linguistic development for children, whereby effectively what you do is you teach the child, or in this case the AI, a word that's completely made up. So you take a word like gigamaroo, and you say to it down here, a gigamaroo is a type of Japanese musical instrument. An example of a sentence that uses gigamaroo, the word gigamaroo is, and I have a gigamaroo that my uncle gave me as a gift, and I love to play it. So yeah, this is amazing that obviously gigamaroo was not in the pre-training, but it's able to actually produce this kind of output. And really, this kind of opened up, and I've got a lot more to say about this as well, John, when I get into the main lecture. But it's opened up what they're calling a new paradigm of computing. So effectively, there's Andre Karpathy again here saying, the hottest new programming language is English. It's the ability for us to effectively create a prompt and then have it answer that prompt, answer our question. So GPT-3 was still pretty much under the radar. There was a few, if you go back and look at the archives, there was like when they produced those things, there was a little bit of news flurry around things like it's going to be able to be used for disinformation and things like that, but there wasn't really that much of a public outpouring. And then, of course, they continued on and took GPT-3 with its emergent properties and its zero-shot learning and things like that. And they started training it even more to actually respond to proper human questions as a helpful assistant, as we know today. And then on the 30th of November, 2022, they released ChatGPT, and 100 million people used it within the first few months. And thousands, not hundreds, thousands of different use cases emerged. And it was like this absolute playground a year ago where everybody was just trying new things and getting it to do stuff that we just didn't expect we'd ever see frankly, in our lives. You take language as being something that is fundamental to put the human condition, as it were. So there's some examples here of things that you can do with GPT 3.5 and beyond. Okay, quickly on prompt engineering. So this is again where I'm starting to run out of time on the chat, but the prompt engineering, you've probably heard the term. We've obviously been giving it prompts all the way through. I've been giving it prompts for all of the images that you've seen on all of the slides that aren't diagrams. But there are some really quite amazing outcomes from these prompt engineering, and it comes down to thinking fast and slow, and asking the LLM to actually think step by step massively improves the quality of the output that you can give it. Things like multi-shot learning means where you not only ask it to do something, but you give it examples. This one here is an example of that. So you give it a question, then you give it an answer, then you give it another question, and this time it's able to actually get the right answer. And this is, we're just starting to learn all of this stuff, and the whole world's learning along with us at the same time. So it's a very, very fascinating time. So I'm going to end today before we go to questions on something that I just put together as an example for John about how the medical, what we can do with just a straight vanilla GPT-4, this is, and a little bit of prompt engineering to produce something that allows us to, what I've just called MedGPT. So this is something that is a 5-stage process. I've already ran it, but you're more than welcome. Anybody on this call is more than welcome to go to that URL and try it for yourselves. But effectively what you do, and before we go into it, is you have a chat phase where you talk to a doctor or a bot about what your symptoms are and what your condition is. And after that chat has been completed, it will then generate some medical notes. So there's a prompt to take that input and then generate medical notes. And then both of these things are passed on to then say, well, can you now make a diagnosis for us? So what exactly is wrong with the patient? And then again, everything's fed into the clinical evaluation and then into the referrals and labs. So it's a relatively advanced prompt, and I do hope this works. I have to press escape, don't I? And move this. Go here. So hopefully that's still visible to everybody. So this is MedGPT on that URL. And rather than type it in now, because I knew I'd be running out of time to show you, you're more, as I say, you're more than welcome to try it for your own enjoyment and interest. But yes, MedGPT is what they call a Streamlit application. So it's just a bunch of Python scripts behind the scenes, and then I've pushed it up onto our website. This was the prompt for this first stage. Effectively, I've given it a mission. You're a patient intake chatbot focusing on symptoms. Your mission is to ask questions and help the patient fully articulate their symptoms in a clear manner. And then it explains what's going to happen to it next. And there's some rules as well I've given it. So very, very short prompt, not much to it. And then I've had a little bit of a chat in this window down here, your message. And I've gone for flu. So I've said I've got a cough, runny nose, no energy, etc., etc. I'm feeling hot and cold. It asks me what my temperature is. I've given it 104 Fahrenheit. It asks further questions. It then asked me about whether I'm producing phlegm, and I had to go off and Google whether or not phlegm is a side effect of flu. It's not. I found out. So dry cough, no mucus. Have you experienced any shortness of breath? And at this point, I've just typed there's a keyword which is done to say I've finished the process. And you go on to the medical notes, and what medical notes does, it's a little bit bigger, but not very much. It just says you're a charting bot, and you've got to take the input and then produce produce the output for them. So here's the transcript of the chat we just had, and then here is what it actually produced as the medical notes in a coherent way to be passed on to the next phase of the bot of the program. So temperature fluctuation, etc., etc. So this is then passed on to the diagnosis stage, which again has a prompt here. This is getting more complicated now. So again, you start with a mission. You have some schema about how it's going to actually get the data as an input. And then this kind of gives you an idea of what I want it to produce as an output. Description of the condition, common alternative names, etc., differentials, demographics, contra indications, etc., etc. So this is what I want it to do. I passed in all of the information you saw in the previous stage. There's the medical notes again and the transcript. And then this is what it produces. So influenza, got it first time, probably because I led it very much down the path of that, COVID-19, et cetera, et cetera. And then it says maybe actually instead of flu, you've got COVID. So I've then given it's that, and it's kind of given us some more information. Please feel free to look at this in your leisure after in the recording. So once you've passed this, we then go on to clinical evaluation, which is another prompt, which is here. And it tries to explain what senses and sounds and further questions that could be asked of the patient and the output format, etc. And then what it's going to actually produce for us. So this produced in this stage, look for signs of dehydration, examination, throat examinations, and interview questions. So when did you start first feeling unwell, etc. These are further things you can ask. And I'd be really fascinated to find out from the people on this lecture whether or not this actually is any good or not. Because at the end of the day, it's not been trained on any particular medical conditions or medical textbooks or anything. It's just raw GPT being asked to come up with some hopefully reasonable questions and things like that. The final thing is the referral. So effectively says I should go and see a pulmonologist and infectious disease specialist maybe, and some tests that could be done as well. So there's the COVID test as well. So hopefully you can see the power of this stuff. Hopefully that was certainly interesting for you guys to listen to. I will be doing something similar to this at another stage for John, where we can go into more medical focused things. How do I get back out there? There you go. So yeah, back into the last part. Oh, so many of these little windows everywhere. There you go, slideshow. Yeah, so you saw the process that you go through, and you're more than welcome to use it. And yeah, hopefully you enjoyed that. And I don't know how many people are on the call or anything, but yes, hopefully you enjoyed that. And if you have any questions, I assume now's the time to ask away.
Okay, brilliant. Thank you very much, Nikki. We've got about 30 people on the call, which is fantastic. Thank you, everybody, for turning up. So just not quite a question, but just in perspective is effectively at the end there, you showed us writing effectively a program. we had some computer program running where the instructions, the programming of it is where you just said, here's your mission and here's a few rules. Yeah. And that's all the programming that was done of that computer, and you ended up with the output for better or for worse. And then the next stage, of course, is that it wouldn't take very much. In fact, we have the technology now, is that you could say to a machine sitting there, hello, here's your mission, and here's what I want you to do, and then go away and do it for you in the same way that we might instruct a human to go away and do something, which is sort of reached that stage. The question now is how good is the outputs, which are getting better and incrementally better and better. Yeah. And as with other parts of AI, particularly in healthcare, and interpretation of diagnostic imaging being a fine example, where the AI has reached a stage where it's generally better than the human interpreting. As a result, nobody training to be a medic these days wants to go and be a radiologist, because they can see the writings on the wall that we won't need radiologists anymore, which is sort of fine. When you reach the stage where it's better, but it's not perfect, then it starts to raise all the ethical issues about whether the better but not perfect AI is something that we should work with, or whether we're more comfortable with humans being imperfect than we are with machines. And particularly from the US, and there's some case law that sets the precedent of this, is that when it's wrong, then who do you sue? Since the creators of what the output is are so many layers of deep, all the people you mentioned who developed the technology, open source software, how you are instructing it to work, that opens up all these issues. So I won't hold, that was not really a question, that was to try and steer the questions we have from the audience now. And officially we've only got 4 minutes left, but I'm sort of assuming that Nikki can stay a bit longer than 4 minutes.
Yep.
So we'll open up for questions and far away. Now I've got everyone that in theory you can unmute yourself and speak, but it would be better if you could just raise a hand if you have a question for Nikki, and then I'll call you out and fire away with your question. I'm waiting for the first hand to appear, which is Millie is our first hand raised.
Hello, Millie.
Okay. Let's see whether this works or not. Millie should be able to unmute herself now. Maybe not. Just 1 minute.
One thing about Millie's my daughter, everyone. One thing about Millie is that she always likes to ask the first question after through a lecture.
Okay.
It doesn't surprise me. I press the button to unmute, but otherwise, Millie, you can always talk to me later.
Okay, we'll have to move on from Millie. So
hi.
Oh no, we're here.
Yeah. Hi, I just wanted to ask, if you so you were complaining about the ethical side of this. If you were to theoretically train in a bad piece of information, such as you train in the training stage, you train in it to focus on a specific medical issue, or to push a specific medication or a specific solution that would benefit a certain group of people, how would you be able to spot that or stop that, or maybe catch that before it affects people at large?
It's a great question, Millie. So you know, frankly, one of the things that one of the directions I do see this stuff going is so far all the way through this lecture, I've explained that GPT's just been trained on everything. It's been trained on literally anything they can get their hands on, which is fine and amazing and eye-opening. But it's not necessarily anything that you would really use as a proper physician or a doctor to actually make any of these type of predictions. So there is a lot of discussion at the moment around whether proprietary or open source models are the way to go. There's because a lot of this stuff is very simple to do. Funnily enough, I know it seems amazing and everything else, but a lot of it is very simple. And within 1 year, the open source community has just about made all of the ground up to where GPT, certainly GPT 3.5, the original ChatGPT and beyond. So there is a lot of worry about being able to train a model to do things that are bad. Not just like state actors, but just general individuals trying to steal your money from a scam email or something like that. I feel though that the real power of this stuff is going to come from where different organizations, different publications, and organizations like that actually train these models on their own data, and at that point they are taking ownership of that data. And I would be willing to listen to an AI doctor from somebody that say the British Medical Journal or whatever it might be has produced, rather than just some random AI model downloaded from a site called Hugging Face, which is where they're all stored. I hope that makes that clear.
Okay, that's good. We've got loads of people with their hands up, so I'm going to go to Megan Lockhart next, since she's the assistant dean, so we better give her a question. I think you can unmute yourself, Megan. No, she can't unmute herself. What is that?
Students ask, you can come to me last.
Oh, we can hear you.
Yeah. Can you hear
Come
me?
on. We can now. Off you go.
Okay. I was saying, let the students and other participants
Oh, okay. That's
ask.
a good question.
I'll be last.
Okay. So who are we on next then? Nabila.
Hi. I was curious to know, this Med GPT that you've built, is it built using GPT-4 where you build your own GPT like that feature they've released, or is it like, what did it entail building something like this?
Okay, so it 100% is GPT-4. Just for the people in this call, I don't really mind saying, but at the moment it's got my own GPT key on it. So every time I run the program, it's costing me a little bit of money. It goes off and runs the inference on OpenAI's servers and then produces the results back. And I would be more than happy to share the source code for this. And it's not very clever, but it works. It does the job. But yes, absolutely, it's GPT-4, the latest model that they're running.
Yeah,
Okay,
because
sorry.
yeah, I was trying to build a GPT-4 where you plug in your own domain, but for some reason it was only letting people who have GPT-4 subscriptions access it. So yeah.
Yeah, as I say, that's the API key. So the API key is embedded in this website, and you shouldn't be able to break out of the MedGPT kind of context that I've given it. But yeah, you do need to either make a decision to put your hand in your pocket and then let people spend your money while they train it or muck around with it. Or the other way of doing it is asking them to get their key. So you can go to OpenAI, create an account, and it will give you a key that you can ask people to use when they use your application. Happy to talk about that offline.
Okay, thank you.
Okay, so maybe this is a good point to mention that Nikki has said there's a longer version of this seminar, which is a sort of 3-hour version that's being offered during our residential course in Oxford next month. So if you're on the call and you're not a student from our Applied Health Informatics program and you think that sounds interesting, then the best way to do that is join the program and do it next March, March 2025. If you don't fall into that category, then we do have a workshop running alongside the Fordham program at Oxford that week, and you can come and join the workshop. So if you're interested in joining the workshop at St Edmund Hall in Oxford, where all this is going on as part of the Fordham program, Fordham's also running the workshop there, then that is something that you can sign up to just for the week without registering for the entire Applied Health Informatics Masters program. Okay, that's an aside to put that into context. Let's go to our next questioner, who seems to be, well, we were doing students. I'm not sure if we've got any students left with their hands up, but we do have Darlington, who is definitely not on the faculty. And so Darlington, off you go.
Yes, sir. Thank you very much. I was just wondering whether you can provide the transcript for this session. Is it possible?
Yes, is the short answer to that. So we've been recording as we go along. In fact, we're still recording, including the questions.
Okay.
So
Yeah,
we'll be posting this up on somewhere in Fordham for access afterwards. Thank you. That's a good question. Who are we up to now? We're on to I think Naveed Dogar question.
Hey, thanks, Nikki. That was really interesting. My question's really small. You know, in the very beginning, when we were talking about training the data set, and you said that every time it gets something right, you reward it, and every time it gets something right, you penalize it in some sense. So I just wanted to confirm, does that come in form of assigning heavier weight to those outputs?
Absolutely, that's exactly what happens. So reinforcement learning means that every time it runs through the network, through the neurons, that path, if you at the end of it, you kind of give it a treat, give it a +1 or a pat on the back or whatever it is that, however you've defined your reward mechanism, means that that weight gets slightly higher. And through that human feedback process over time, over hours in days and months, etc., of running this stuff, that's how the neural net starts to give itself weight and biases. Yeah, absolutely, that's exactly how it works.
Thank you.
So the long answer to that question is that there's various algorithms of various degrees of sophistication of to how you go back and adjust all the weights which are on the links between the neurons, and you can do that in a recursive way. So you go back and work out the rewarding for, if you like, bad answers is made by taking the difference between the answer you received and what you were expecting, and then feeding that difference back through the network, and then adjusting the forwards all the weights to get to the answer that you were expecting. You can only do that if you're training by telling the network what the correct answer was, in which case you're doing some sort of supervised learning. But one of the big breakthroughs in the last 10 years or so has been unsupervised learning, where you don't you're able to reinforce but without saying actually what the correct answer is, and the neural networks can learn the categorization. I think Nikki gave some examples there, where if you look within the hidden layers of the network, you can start to see where neurons in that network have become specialized for a particular function. Which is sort of quite an amazing thing, and we think that you would imagine, which I think is true, that that's exactly what's going on inside our brains. So if you roll back this to the original mathematical models of the central nervous system, which from the early 1940s, and then into the development of things which is called the perceptron, which is Frank Rosenblatt's original one neuron network, and then connecting those together. The original plan of that research was to make computers which mimicked the operation of the central nervous system, and it looks as if, having done that, we collectively have been able to not only mimic the central nervous system, but actually then observe behaviors in the mimic of the central nervous system, which would appear to exactly correlate to what's happening within a human brain. So you have to assume that those original models and everything based on it must be a fairly accurate model of what's happening in reality in the human central nervous system. But anyway, sorry that I hold the answer to the question, but part of the answer to that question is that the algorithms for the feed forward networks and the recursive networks of learning are not quite as simple as just adjusting the weights, and the more sophisticated the algorithms and statistical techniques that you use in the training methods, the better the results you get, which is where part of the dark art of the training the network comes. Right, so that was taking up lots of question time. Let's have, I think we are ready for Megan to ask a question now.
You're ready for me, huh?
Yeah.
Thank you, Nikki, for this talk. So I guess I'm really interested in this stage right here on the screen, the diagnosis, right? And just to kind of give you some context for my question, I'm a neurobiologist by training. Okay. Not just human brains, but brains in general. And the way I like to think of like where the real potential for AI is, you know, what human brains are good at doing and what we're not good at doing, and how to complement the things that we're not good at doing, right? So for example, we're really bad at nonlinearity, right? And so the way that human brains deal with linear or non-linearity is we zoom in and we are able to approximate linear, right? I think AI has tremendous potential for that, for scale. I think AI has, I think we have very low RAM, our computational systems, right? And AI has, exceptional RAM, right? And so one of the things that, like, with these kinds of applications that always sticks with me is, if I just kind of break down what really good clinical decision making does, right? One is that, the outcome and the decision are different, right? You can make a good decision and have a bad outcome. You can make a bad decision and have a good outcome, right? That's just because of the uncertainty, right? Uncertainty, and to some extent the statistical nature of biology, especially, right? So, like, how do you build that capacity of being able to parse the quality of the decision from the outcome, right? Which I feel like medical doctors do as a group. Like, they spend a lot of time in grand rounds and stuff, like really looking at cases and trying to analyze this and like collectively get better, right? The second thing I think really good clinical decision making is it again, and this is about like being able to handle uncertainty, right? It's like, what is the probability of this diagnosis, and this diagnosis, and not just the probability, but also what are the consequences if I'm right, and what are the consequences if I'm wrong, right? And so a clinical algorithm tries to rule out sort of the more serious outcomes, right? Before proceeding with a plan. So there's more space to gather more information, potentially see, like, for example, how a patient responds to a certain medication, right? So I'm curious then, like, is it possible for a format like this, right, to kind of be able to build in information about the model certainty in the diagnosis, right? And then also sort of weight, like some kind of weight for different outcomes, whether that's like you kind of go back to a more traditional confusion matrix and look at, recall and precision and, all these different sort of measures of how well the models perform and that weight those different consequences differently.
Fantastic, absolutely fantastic. The kind of poker hand, what you're saying there, you could play an absolute exact poker hand and yet still lose, as it were, is definitely something that, remember, these are just at the moment very kind of simplistic simplistic models that are just pushing out exactly what it's on its mind at that moment in time. It's this very much this kind of thinking fast and slow approach. And some of the stuff that I'm absolutely going to cover in the workshop in March is around the advancements that people are making in the idea of having multiple agents involved in the process that are all designed to do different things in making that kind of diagnosis, as it were. They call the technology mixture of experts, and the idea is that you have in some of the open source models like 8 different experts, and they all do different things as part of the decision-making process. So really, we are at the start of this. It's only been out a year or so, and people are starting to see how we can apply it in different areas. But it would be wonderful to actually sit down and think about how you could actually map this out in a way of saying, yes, you're giving absolutely the right diagnosis, and yet the outcome is different, and then feeding all of that information back in on itself. And everything. So yeah, it's a fascinating field, and I think nobody really knows the answers at the moment completely, and it's a bit Wild West. I wouldn't certainly be using this in its current format for doing anything, frankly, until we've until we know that exactly what the model contains. But I think the problem itself has been broken. So the straw that kind of broke the camel's back was the transformer architecture, and being able to actually start to say you can keep an awful lot more information and train an awful lot more information within the size of the RAM that we've got available to us in these cloud computers. What we do with it is up to us now. I can. Again, can take it offline or whatever. Or I'm certainly going to cover it definitely at the next workshop seminar, whereby we go into how you can chain these things together in such a way that before the answer goes back to the student or the patient. I'm thinking very similar things with some of the stuff we're having to do with students, and trying to kind of make sure that they don't just ask the bot or the AI or whatever to just do all of their homework. You have to have multiple layers in there. So yeah, it's a fascinating field, and I'm really looking forward to seeing how it kind of evolves.
Okay, thank you, Nikki. So we've run quite a lot over time, so I'll just give the last question to Jim Couch, who actually is a human medic. So let's see what he thinks of it.
Great. Can you hear me now?
Yeah.
Terrific. Okay. As I said, John, great to see you. And Megan, everybody, Naveed too. As John said, I do teach in the AHI program in Oxford in September in health data analytics leadership. I'm a physician. I believe in the old adage, physician heal thyself. For the last 20 minutes, I've been using your MedGPT program.
Oh, right.
For my indigestion that I felt for the past month that I've been doing my taxes. So I put in all of the appropriate symptoms, and I think it was really quite accurate at making the diagnosis, because since I filed my taxes 2 days ago, I've felt markedly better. So I just wanted you to know that your program is great. I wish I had a primary care physician that was so attentive.
And the thing is, the thing that I find so funny about it is that it's not, from an insurance and all of those kind of viewpoints you'll see on the very first page I've put on there, do not kind of sue me for anything. I'm just just putting this out there, as it were. Right. But it really does seem to lower the barrier to entry to people. That's where I kind of see this AI stuff going, is that you don't have to you go out of your way to actually use these things, and how for simple things, is it going to be able to help people in mental health? There's a lot of studies at the moment in using these AI bots to just kind of do what a normal psychotherapist would do and things like that. So it's a very interesting time, James. Yeah.
Yeah, my wife, who is also a physician, and some of you know her, she's been on me for the past month to go see my doctor, which I haven't. So I've been trying to treat myself. And so actually I would say that what I've just done with your MedGPT program has reaffirmed what I've been doing is the proper course. So I will show this to her when I can.
Okay, I think that's a very appropriate way to end. So we've seen Nikki create a doctor by telling ChatGPT to can think it's a doctor and diagnose patients. We've had a doctor use it and say that it's great. So that's the end. We've done our quality assurance as well. So thank you, everybody. That was the first in a series of seminars which are going to run not quite every Thursday, but for in the next month or so, most Thursdays at the same time, place to be as will be advertised. Thank you, everybody, for turning up, particularly people who asked questions. The transcripts, which we can ask, in fact, we should generate the AI transcript of the whole session, I think would be appropriate, but the recording of it will also be available on somewhere on the Applied Health Informatics pages at Fordham. Thank you, everybody. That's it. Have a great day, and thanks for joining us.
Thank you.